Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN, sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
So I'll kick it off. So hello, everyone. Welcome to this session. My name is Arnaud Devos from ALICE, the European Laboratory of Learning and Intelligent Systems. And we're super happy to have with us Professor Daniel Cremers for today's session. So a short intro on Professor Cremers. So Professor Cremers is a professor of computer science, technically informatics and mathematics at the Technical University of Munich. And his research interests circle around computer vision, machine learning and deep neural networks, mathematical image analysis, and other things. And previously, he also was mentioned from 2020 to 23, listed as the top 10 most influential scholar in robotics of the last decade. And he also has been the president since 2023 of the European Computer Vision Association. With respect to ALICE, he has been the ALICE unit co-director of Munich, and also since more recently, the Elias node co-director. So with that intro, I give it now to Professor Cremers. Please start. Thank you.
Thank you, Arnaud, for the introduction. Thank you also to the organizers of this amazing series for offering me an opportunity to present our research and our insights into AI in this series. I spent some time thinking about what might be a good topic for this series, and I decided to talk about convolutional networks beyond the Euclidean space. But before I go into that, let me start with kind of a more basic kind of, let's say, my beginnings in the field of AI. And also showing you a little bit what are the challenges in artificial intelligence. One of the things that we've been working on for over 20 years now is driver assistance and autonomous driving. So laying the foundations for autonomous driving. You see it here. This is a recording we did in 2005 where we put cameras in cars and we started recording what's happening around the car, in particular in front of the car. And obviously, the aim would be to develop algorithms like the ones we did starting in 2006 and later, algorithms that take this video footage and can recover the 3D structure of the world and the movement of things here color-coded, right? And this color code, this movement is vital because it allows you to make predictions as to if this same obstacle keeps moving at the same velocity, it will be in the driving corridor in the next few seconds. And you can imagine that the longer I can anticipate into the future what will happen next, the better I can avoid accidents and save lives, either by sending out a warning signal to the driver saying, careful, there's an obstacle coming your way, or by actively engaging in the braking maneuver. And so this was the ambition that we had. And what's behind all these techniques that we developed is this whole concept of artificial intelligence. And that raises a little bit the question, what is really intelligence? What is artificial intelligence, right? And everyone has different views on it. Traditionally, people would have said someone who can play chess, that's a form of intelligence, right? A person that can play chess well is, one would say, is intelligent. And so reproducing that capacity is an ambition that people have had, and in fact have had for centuries. This is something a lot of people don't realize, but this dream of creating machines that can somehow reproduce human capacities and human intelligence has been with humanity, I guess, ever since the beginnings. Here's one such example, a system that's often referred to as a mechanical Turk. This was a chess machine in a way that was conceived by this guy named Wolfgang von Kempelen in 1770. It was a machine that allegedly could play chess, right? And you see how it worked. They actually had a human chess player inside it who moved the pieces from inside. But it was presented at these shows, much like in a magic show. They would open the front and say, there's no one here. Then they would turn it around and then open the backside and say, there's no one here either. So that people had this illusion that it was really a pure machine that was moving the chess pieces. And a lot of the grands of the time, people like Napoleon, actually played against this chess machine. And even though in retrospect it was not real, you can see the fascination that humans had with a machine that could do something intelligent. And that's kind of a dream that humanity has always had. And that dream with respect to chess playing became reality. You know, chess players have been around for years, but in 96, IBM's Deep Blue managed to beat the best human chess player. And the way this worked was essentially it was able to compute or evaluate 126 million configurations per second in order to decide what was the most likely configuration to win the game. And for me, this was never really a surprise that humans were beat by a machine, because I grew up in the 70s and 80s, and in 82 this computer came out, the Commodore 64, and I got one such computer. So in my teenage time, I started coding with this computer. It created my first fascination for computers in the first place. It actually came with this tape player that I had. So, I have very fond memories of it. From today's perspective, that computer is considered miserably slow. But for me at the time, it was amazingly fast. It was mind-blowing what the system could do in such short time. And this Commodore 64 came with lots of games, in particular with a chess engine. And so I could play chess against the computer. It came with, I think there were 7 levels of difficulty. And on level 2, the system always beat me. And so I never really tried levels 5, 6, 7 because it was pointless, right? And so admittedly, at 14 or whatever age I had, I was not the world's best chess player, right? But, for me, it was very clear even back then that it would only be a matter of time until these machines would outperform the human. And so they did in 96 for chess and in 2016 for Go, beating the best human Go player. But then, you can start wondering, is that really all is that really intelligence at its core, right? This ability to play chess. Because then if you think about it, humans, they don't come into this world with the capacity to play chess. Chess is a very artificial kind of strategy game. It's not something that the human brain and mind was designed for by evolution. But there is something that our brains were designed for by evolution, and that is making sense of our world. And for me, and this is one I want to bring across here, this is really the heart of artificial intelligence, the capability to understand our world with our senses and to understand and reason and predict. So this is an example, right? This is a picture I took. I gave a talk in the German museum the other day, and this is the museum shop. And when I came in, it was already closed, but I took the snapshot because something that always strikes me working in this field of image analysis and computer vision is how amazingly talented humans are. And we have this skill and this intelligence to understand the world through our eyes at a level that we're often not even aware of. And so I want to bring that across here because this is very central to image analysis and computer vision. What do we do when we look? We look into this shop and we see, a picture of an elderly man. This is clearly Einstein. But we do that in fractions of a second, right? That we analyze the scene, right? So let's look at this more closely. Let's take this image of Einstein and let's zoom in a digital image. All of these images are stored in form of pixels, as you know, brightness values that can be encoded with numbers, right? And so this little patch in Einstein's eye in the computer, it looks like that, you know, different values for different brightnesses from left to right. And so the whole image is a huge matrix of numbers, right? Now, if I were to present you this matrix and ask you, what do you see? You know, do you see Einstein here? Most of you would say, well, that's not really what I see. Well, yes and no. It is exactly the same information. It's just not encoded in the way that your brain is used to it. But every number that you see here corresponds to the brightness, and so all the information you need is there. It's just not prepared in the way for our brains to process it, right? And the question is, how do we solve this problem? You know, and you know, neuroscience isn't really that far yet to fully understand how the brain works, but it's always been an inspiration to AI and machine learning. And so, you know, one strategy you could think of is, why don't we memorize the brightness values? And if the same set of values comes again, we say Einstein, and if not, then not Einstein, right? But obviously, that's not going to work, right? If I move the camera, then all these values are going to shift accordingly. If I rotate the camera, the numbers will rotate accordingly. And if I zoom in or out, then all the numbers will shift around again. And then if I change the lighting in the room, or if I take a different image of Einstein, or if Einstein wears different glasses, then the numbers will change again, right? To the extent that you cannot just memorize the numbers. And this is a riddle, and this shows you that, you know, understanding the world from images is actually far from trivial. And if you go deeper into neurosciences, you find that the human brain, for example, dedicates half of the cortex is dedicated to processing visual information. In other words, we dedicate roughly half of our brain capacity to processing images and what our eyes see. That tells you two things. It tells you that, first of all, clearly the challenge is not easy. Otherwise, we would not sacrifice so many neurons on this task. But it also shows you that this challenge is important. We get our understanding of the world we live in through our senses, and in particular through our eyes. And so to reproduce that, this is really what computer vision is about. And recognizing objects in images, Einstein, faces, cats, dogs, whatever, this is one of the challenges in computer vision. And it was really propelled by a data set that a friend and colleague of mine, Fei Li, put out a few years back. It's a data set called ImageNet. It's a data set that contains roughly 14 million images of different objects. Different classes of objects. Typically, each image has one dominant class, dominant object. So here it would be the Dalmatian dog. But then there are other classes in this data set that are not as obvious to humans. This one, for example, is a fruit named, you will probably recognize it. Some of you may, some of you might not. It's a fruit that's not very common in Germany. So most Germans have a hard time recognizing the object here. It's called physalis. But what you can do now is, much like with chess, you can have the machine compete against the human, right? And so you will select a set of randomly chosen images from different classes, and you will ask, what class is this? What is the dominant object in this image, right? And then if you did this in 2011, the machine on a given set of images would make 26 mistakes, whereas the average human would only make 5 mistakes in classifying what the dominant object was, classifying the image, right? And at the time, it seemed impossible to ever get anywhere near human level performance. See that the error is 5 times larger, more than 5 times larger, and performance was stagnating up until something, in retrospect, almost magical happened. Alex Krizhevsky and collaborators advocated the use of a deep network to process this challenge, to tackle this challenge. Deep networks had been developed for years, first shallow networks, then deeper networks, but this was kind of the marks, in my view, the breakthrough of deep networks. Why? Because on that important challenge, they managed to significantly reduce the error to 16.4 in 2012 with what is now called the AlexNet, based on Alex Krizhevsky. And that was obviously a massive breakthrough on this challenge of image classification. And so in the wake of this paper, everyone started focusing on deep networks, developing more and more sophisticated network architectures, deeper, more refined architectures that process these brightnesses that go in on the left, and then, layer by layer, they get filtered and processed by typically convolutional filters up until the end, you get a classification output. And this, not surprisingly, has become one of the most influential papers in computer vision and in the sciences. In general, it's been cited in the last, decade or so, more than 185,000 times. So this is one of the most influential publications I am aware of. And to some extent, justified, I think, is the fact that there are two pioneers who were awarded the Nobel Prize for Physics last year, John Hopfield and Geoff Hinton, who, among many others, pioneered a lot of the ideas that made this happen. And for me, this is really the breakthrough of artificial intelligence, because we were able to, as you can see, in 2015, beat the average human, not on a contrived task like chess playing, but on something that arguably the human brain was designed to do, understanding the world from our senses, right? And so this is where the real breakthrough, in my view, of AI started and happened. Now, in the wake of this paper, the question is, what is this good for? You can obviously detect objects in images, but for example, in terms of social good, one of the things we did in 2019 is we showed that you can classify images that for humans are not so easy to classify. Obviously, everyone can detect a cat or a dog or an airplane, but if I give you these two images of a chest x-ray and ask you which of the patients has tuberculosis and which one doesn't, you would have a hard time. Admittedly, you're likely not a radiologist, right? Radiologists who do that every day, they will perform better. But in a way, the human brain by evolution is not really trained to process x-ray imagery and is not really trained to identify tuberculosis, right? Cats and dogs, yes. Why? Because we need to recognize the lion in front of us in order to survive. But recognizing whether someone has tuberculosis from an X-ray image is not something we are born to do and we learn to do, right? But you can train a neural network to do it, and it will tell you this one is tuberculosis and this one is healthy. And you can go further and train the network to actually tell you which are the salient areas in the image that led to this decision, so that the radiologist can validate, is it really true? Where did the system really look? This is important for reliability and trustworthiness, that we not only get a decision, but we get some understanding of how did the machine come to this decision. And then you can compute receiver operator curves and show that this actually works amazingly well. But this is, again, image classification. And one of the things that I and my team started looking into very early on is, what other challenges can we tackle with deep networks beyond image classification and beyond Euclidean data, images being in a Euclidean space, right? And this is a little bit the focus of this talk. What we showed, for example, is in 2015, we introduced a technique that we called Q-space deep learning that allows to dramatically accelerate MRI scanning. For diffusion tensor MRI, we showed that you can get the same quality scan by this Q-space deep learning, so a deep learning enhanced scan, such that the patient can spend 12 times less time in the scanner for the same quality result. And this is important. If you've ever been in an MRI scanner, you will know This is not nice. You spend like 20 minutes lying in this tube. A lot of people get somewhat claustrophobic. So if you can reduce the scan time by more than an order of magnitude with a deep learning enhanced system, obviously there is a massive value in it, both in terms of the value for the customer, but also obviously in terms of cost, right? We also showed in 2015 the very first deep network to predict movement in videos, so-called optical flow. This is a technique that we called FlowNet, and that is now at the core of pretty much every optical flow method today. They all essentially go back to this very first FlowNet that we published in 2015. So you see, we were quite early exploring the realm of what else can we do with neural networks. We then went further in 2016, showing that beyond flow, you can also predict depths, stereo, disparity, and 3D flow from stereo videos, scene flow, using suitably trained deep networks. And we went well beyond image analysis. For example, in 2016, we showed that you can tackle this very important challenge of protein prediction from amino acid sequences with a suitably trained deep network. And since this has gotten a lot of attention in recent years, let me go deeper into what we did in 2016. This was an oral presentation at the flagship machine learning conference, NeurIPS, the #1 conference in AI and machine learning. The challenge we set out to solve was, given an amino acid sequence, for example, from Homo sapiens here, can we predict the 3D structure of the protein that it encodes? How did we propose to solve this challenge? Well, we tapped into a database of amino acid sequences from other species, sequences with known structure. And we identified similar sequences by a multi-sequence alignment. Then we computed pairwise variance of mutations, so seeing where do we have pairs of mutations along the sequence. And from that, we computed what's called the co-evolution statistics. And then that was the key idea, really. Some of these components were there in 2016. The key idea was to say, can we train a deep neural network that predicts right from these co-evolution statistics the contact map that encodes the 3D structure? And now, for those of you that work in this area, or those of you who follow the media, this might look familiar to you. It should, because it is the precursor of AlphaFold. Google AlphaFold, the first paper appeared, I think, 2 or 3 years after ours in 2018, and then 2021, that was 5 years after our paper. AlphaFold, if you look at it, follows very closely in our footsteps. They adopted our pipeline to a large extent, refined a lot of the elements, the aspects, through more training data added, because a few years later there was more training data available, more GPU power to train, so they got further improvements in the performance. But the key pipeline was already in our paper in 2016. And I recently posted this on LinkedIn, and even people from the AlphaFold team said, oh my God, how could we have missed your paper? Because the thing is, they didn't actually cite our paper. And then that I find not so surprising. It happens that you overlook important prior work in science. What I found a little bit more surprising is that they ended up getting the Nobel Prize for this. But to go deeper, what did we do? We actually trained a network. Here's an example. On the left is the ground truth contact map for a protein from the test set. And on the right is the predicted contact map with our deep network. And then we did a quantitative evaluation on the CASP data set, something that you typically do, showing that our method actually outperformed the entire state of the art significantly, especially, as you can see here, on medium and long sequences that were considered the most challenging. And also compared to methods like metapsychov, methods that actually use additional information, not just the amino acid sequence, but more information, and ours that only use the amino acid sequence still outperform them. And so I think we actually also demonstrated the breakthrough of what you can achieve by tackling this protein prediction challenge with the convolutional deep network. Let me move back into my main area of research, computer vision. One of the topics that we work on extensively and have worked on for many years is the reconstruction of the world from cameras. Here you see such a system from just one single gray value camera, much like you have it on your smartphone. We can in real time reconstruct large-scale worlds with practically no distortion. And that was in 2014, entirely unheard of in the vision community. And so just last year, this work received the ICCV 24 Test of Time Award as the one paper from 10 years earlier that stood the test of time. It is a technique that allows you to create a virtual copy of the world. We'll see more of it along the talk from just a camera. This is very important for autonomous systems, for self-driving cars, but for augmented reality and many other applications. Here's a more recent work along these lines from 22, where equipped with a camera, much like you have it on your smartphone, we go up into our building to the 3rd floor. You see the video on the bottom left. And then we go into a tube. It's a slide that takes you 3 floors down. And you can see the slide is fairly dark. There's very limited visibility. And yet our system, as you see on the big screen, can track you at completely unprecedented precision and robustness, where we can go back 2 flights of stairs to the 2nd floor where we started. So we've gone up and down 3 flights of stairs and gone through a tube, and you can see there's practically no drift. There's practically no offset. So the precision of tracking you with just a camera-based system is very unprecedented. Now you can deploy deep networks for these kinds of challenges in many ways. For example, one thing we did a few years back is we put cameras into cars and then showed that in real time we can generate not just maps of the world, but semantic maps, as you see here, where we can distinguish by color the different objects, the drivable area, the sidewalks, the cars, the vegetation, the buildings, whatever you want, right? Stop signs, you name it, right? And this is important because it allows us to create massive scale semantic maps in just a few hours with a fleet of cars that have essentially cameras in them, right? So at very low cost, we can copy and create digital twins of the world that can be used for autonomous driving. And I think with the research we've done, we've established the camera as the lead sensor for 3D perception in autonomous cars. And as you may know, a lot of autonomous cars to date are still relying on LiDAR, laser-based scanning. With our algorithms, these LiDARs are becoming obsolete because we can take one single camera, as you see here, and drive through the street and then create what you see here, a virtual copy of the world that we can compute in real time from just one single camera. And maybe the precision of this point cloud is not quite on par with what a LiDAR scanner could give you, but I would argue it's sufficiently precise to allow obstacle avoidance, path planning, and anything you might want to do in the self-driving world. And so with these kinds of techniques, we are really establishing the LiDAR sensor as the lead sensor for understanding and capturing the 3D world. And not just large-scale worlds for self-driving, but we have developed techniques, and you see this is even 12 years old, techniques where with a single camera and a single turn on a chair, you can get in real time a complete dense colored copy of a human that you can then upload to a 3D printer. I'm sorry, the video is a little bit slowing down, but you can create virtual copies and physical copies with the 3D printer of people. let me move on. Here's more examples. You see on the top scan systems, this is the former president of TU Munich. This is the Bavarian prime minister on the right side. And we can create copies of people that are sufficiently precise so that you can actually recognize the people, right? And so you can create digital copies of people, static people, but even dynamic people. And you see this again is work that we did more than a decade ago already, showing that we can reconstruct actions from video like you see it here. Right? This is a rope jumping girl filmed at the INRIA in Grenoble by Edmond Boyer's team. And you see, we can take these synchronized videos and we can reconstruct the action at a level of precision where the entire rope of the rope jumping girl is faithfully recovered. And that can be used for sports analysis or for other things. For example, you can record actions like this one here of two athletes, well, gymnasts or semi-professional gymnasts. There's still room for improvement on the cartwheel, I would say, but you can use these tools to really analyze the movement in 3D. And not only that, but you can freeze time, you can pan around like you see here, and then you can even project the colors back on, and that gives you a virtual video of the action, right? It's like what's often called free viewpoint television, where I can hallucinate what would the action have looked like if there had been a camera here. I have a complete reproduction of the action in the computer. And this is something that a lot of Hollywood movie makers are out for, this feeling of immersion, that the customer can watch an action like this one and in real time at home pan around in the action and decide from which vantage point to view the action and to literally walk into the action like you saw it here. But with 3D reconstruction, this raises the question of analyzing and understanding the 3D world. This is something that we humans are notoriously also very good at. If I show you two objects like these, and you will see a similarity, right? You will see that these two objects are similar, even though they're actually in detail fairly different, but on some scale they are similar. We see a correspondence, right? We see which point on one shape corresponds to which on the other. The challenge is, can we perform this 3D understanding in machines? And this is something we've looked into for many years because I think once we recover the 3D world, we need the machines to not only recover it, but to understand it, to make sense of it, right? To see similarities. And we found algorithms like this one that allow you to find a correspondence even between objects that are very different, like a horse and a dog, or even a horse and a human. And you can see we can compute the correspondence across these shapes, where the color encodes the correspondence, where even the toes of the human are put in correspondence with the horse, and the head and everything is put in correspondence with everything else. And so this is something I want to discuss now. How can we interpolate shapes? Let's say we're given two shapes like the gray shapes here, left and right. Can we create a family of intermediate shapes? Can we interpolate? Can we compute correspondence? And can we do that with a deep network, such that given just two shapes, the machine will be able to hallucinate what happened in between, and hallucinate a lot of differently articulated humans from just seeing two humans. This is very much about understanding 3D shape and its movement in time. And once you do that, given the first and the last shape, you can actually create entire videos of deforming shapes that are entirely synthetically generated by the machine. How can we deploy deep networks for shape analysis? Well, it turns out we can do that by realizing that the shape is a graph. And then we can have graphs, and we can apply graph convolutions, edge convolutions, and other type of operations to extract features on the graph and also to interpolate. And then we can train this neural network to do graph convolutions and graph filtering such that we can deform one shape over time into the other. I highly recommend, we have a cat. If you have a cat, do not do this at home. Cats do not like to be moved in this fashion. I know ours doesn't like it. So this is not really biologically plausible in terms of the bone structures, but it is plausible in terms of the shape deformation here. And the way we did it, as I showed you, is by basically identifying the shape with a graph structure and applying graph convolutions. And this is an established idea. And in fact, a lot of data in the world can be represented in form of graphs, not just shapes, but molecules, other kinds of structures, proteins, etc., can be represented as graphs, right? And I'm sure many of you might be working on graph data. But once you look closer into this, you find that the majority of these graphs will be directed graphs, actually. For example, the internet is a directed graph where you have web pages that link to one another. You get a link from one web page to the other, but maybe not vice versa. And you might want to understand, how frequently do people typically go from this web page to the next web page. You want to do statistics, you want to do predictions, link predictions, the interaction predictions. How do users behave on the internet? These are the things that you want to do. In addition, social networks are an example of directed graphs where you have, for example, I recently joined this social network. It's called Blue Skies. And to date, it seems that I'm following everyone, whereas no one is following me, right? So this is a clear case of a directed graph where it's not symmetric, right, necessarily, or transportation networks. And again, this is important. Why we want to understand how people interact and behave on social networks. We want to develop machine learning tools to understand human behavior, predict and anticipate, etc., in social interactions. Transportation networks is another example where you have roads, often one-way roads that lead from A to B, but not necessarily back. And you want to predict traffic and you want to predict congestions and things like that. Then there is computer networks, right, with routers, etc. And you want to predict traffic on these computer networks. But also project management is an example of a directed graph with tasks and dependencies, etc. And then, if we want to encode the knowledge in our world, there is a popular framework called knowledge graphs. And these are also directed graphs that allow us to represent things in our world and their relationship and their interactions, right? And if we want to do machine learning for these applications, we need to devise techniques that allow to generalize convolutional networks to directed graphs. How do we do that? Well, let's start with graphs. Here's the classical convolution on an image. You all might be familiar with it, I suspect, where you have these filter kernels that you shift left and right, up and down to compute the output of a convolution on an image. Now, if you have a graph, that doesn't work. There is no left and no right. There is no up and no down. And so this idea of a sliding window filtering operation does not generalize to graphs. That's bad, so we have to come up with better ways to extend convolutions to graphs. There are two established alternatives. One is a message passing approach that was popularized by Kipf and Welling. And one is a spectral approach that was popularized among many others by de Ferrar and collaborators. So let me look into these for a second to show you how they work. You might already be familiar with them, I don't know. So the message passing approach is essentially you train neural networks that do message passing iteratively from nodes to edges and edge to nodes. So they have update operations where you update the value at the edges using the nodes, and then in alternation you update the value at the nodes using the edges, right? And you train neural networks to do these updates, and then you pass messages in this fashion with these iterative operations. This works nicely and it's very popular. There are some shortcomings. First of all, this message passing is strictly speaking not equivalent to a convolution. And secondly, it's often hard to capture long-range interactions in a network between very distant nodes by this local passing of messages. So the alternative, and very popular as well, is a spectral approach. And this approach is based on the simple observation that anyone with a bit of math background will remember from college, that a convolution is nothing but a multiplication in Fourier domain. So you take your input signal f, you do a Fourier transform, then you multiply the frequencies with a filter kernel G, and then you do an inverse Fourier transform to get back the origin to the original space. And then you can observe that this Fourier transform is nothing but a projection on the Fourier eigenfrequencies, either sine and cosine, or these complex exponential functions, right? And then you can observe that these exponential functions are the eigenfunctions of the Laplace operator. And this is really nice, but because that allows you to connect to graphs. Once you have a graph, you can define the graph Laplacian, and you can compute its eigenfunctions, right? And you take these eigenfunctions, let's call them phi k, the eigenfunctions of the graph Laplacian here. And then you do a projection onto these eigenfunctions that corresponds to a Fourier transform in the graph. And then you do you can reproduce the graph convolution by multiplying these eigenfunctions by respective weights. So this is the multiplication in Fourier domain, and that way you have a perfect reproduction of spectral filtering for graphs. So far, so good. Big drawback, this approach only applies to directed graphs. Why is that? Well, if you have an undirected graph, then the adjacency matrix and hence the Laplacian will not be symmetric. And if you remember, basic linear algebra, you need symmetry to have a complete spectral basis. Something that I often check in interviews when I interview candidates. If you have a symmetric matrix or a symmetric operator, you are guaranteed a complete spectral basis. If you don't, then you don't have that guarantee. And that's a problem because it means this approach where we project onto the eigenfrequencies and then rescale the eigenmodes with this filter kernel G, this approach with the spectral basis of the Laplace operator, here the functions phi 1 through phi n, this doesn't apply because we don't have a spectral basis. So we cannot perform this operation. And so for the longest time, the community was convinced that spectral convolutions do not extend to directed graphs. Up until last year, my student Christian Koke found a way that actually allows you to extend spectral convolutions to directed graphs. And so this will open up Pandora's box of applying deep networks to directed graphs. How does it work? Well, he said, let's observe this mapping as fundamental, the mapping from X to some operator G operating on the Laplace operator, the graph Laplacian, right? And we want to know how can we represent and then learn this operation G of Nabla. Sorry, not Nabla, the Laplace operator. And so what he did to make life a little bit easier, he said, let's consider functions G that are holomorphic, i.e. complex differentiable. And for me, that was beautiful. I love mathematics, and my favorite class in college was complex analysis, but I found it fairly useless in practice. I never thought that this could be really applied to any real-world problems, or very little, up until Christian showed me that this functional calculus actually allows you to define operators on the graph Laplacian. And it uses this classical result from functional calculus called Cauchy's integral formula that allows you to write the value of G at some value lambda as a path integral on a path around lambda. And this is important. It actually extends not just to complex functions, but also to operators T. And so we have the same kind of path integral formulation. And then what we can do is, given an operator and its spectrum, its eigenvalues, we can define a path that includes the spectrum, and then we can compute G for any t in this fashion by evaluating this path integral. And the way he does it is he considers a parameterized function, a parameterized convolutional filter with a set of weights, theta I, and these eigenfunctions, some basis psi I, for example, the polynomials or something. And he shows that if you use the polynomials, then also it is a polynomial in the operator t that you get. So this is very nice. And so this gives you a very principled way to extend convolutional filtering to directed graphs using this holomorphic functional calculus. I don't want to go too much into details, but you're welcome to look into the paper to read about it. But what's nice is it not only offers a very principled way to do graph convolutions on directed graphs and spectral convolutions on directed graphs, but it actually outperforms, as you can see in this exhaustive evaluation, it outperforms all existing approaches that were often a little bit engineered to make them applicable to the directed graphs. This so-called FaberNet, a particular instance of the HoloNet, actually performs better than all the baselines. And this shows once again that a rigorous principled mathematical approach is often favorable also in terms of the practical performance. As people say, there is nothing more practical than good theory. With that, I come to the conclusion. I talked about the breakthrough of convolutional networks with Alex Krizhevsky's application to ImageNet. I talked about, applications of convolutional networks to tuberculosis screening from X-ray imagery. And then I talked about a multitude of challenges beyond image classification, including protein prediction, which we solved in 2016. Then the dense reconstruction of the world from cameras that you can train deep networks to help you do it. Shape analysis, where we can compute similarity between 3D shapes, where we can compute correspondence and interpolate 3D shapes. And I talked about a rigorous mathematical framework using holomorphic functional calculus to extend spectral filtering to directed graphs, showing that this actually leads to a significant improvement in performance compared to existing methods. That's all. I thank you for your attention.
Awesome. Thank you so much, Daniel, for the great presentation and a walkthrough throughout the history of recent AI and some older AI and some newer AI. And super exciting to see about these, directed graphs, convolutions, and everything, and how it will probably become the future of AI. So now also the floor is open for questions. I'll start off with the first question, and then also welcome questions from the audience. So you mentioned this, that it's applicable to many things, like in a way, these directed graphs are kind of generalizations of the very solid matrix that we use to operate in the Euclidean space. But now there's also a wave of like relational databases, which much of the world runs on, and that can also be seen as a directed graph often.
Oh, yes.
Do you have any nudges what the next advances in that direction are? Because they could also bring about like massive impact, because all software runs on relational databases.
That's a very good question. So I think we have only scratched the surface with our work on what are potential applications in chemistry, in protein analysis, things like that, in molecule analysis. But obviously, relational databases is an important challenge. And I mentioned all the different challenges in society. This is very funny, but once you have this concept of a graph, and the concept of a directed graph, and you start looking into the world, you see graphs everywhere. This is symptomatic for anyone who works in machine learning. A lot of people are flocking towards graph neural networks because they realize that, beyond images, a lot of structures can be represented with graphs, right? And then if you have the right tools to process graphs, then this is the future, right? And as you say, relational databases is an example of a directed graph. So I'm convinced that this framework can play a crucial role also in machine learning for relational databases.
Makes sense. Oh, we have a question from the audience. So if you could suggest what we could do or learn with CNN or any neural network in computer vision, specifically for 2D pictures or satellite data for the next 5 years, what should it be?
I think, understanding images with convolutional networks, I would say it depends if you're working more on the application side or more on the theory side. My side is probably more on the algorithmic and theory side. And I wouldn't say it's a solved problem, but convolutional filtering of images is now very well understood since the first works that, Alex Krizhevsky's, but also earlier works by many other researchers in the field. We have a very thorough grasp of how to process images with convolutional networks. And I think one of the messages of my talk is there is a lot of potential in expanding the power of deep networks beyond images, beyond classification, to do 3D analysis, understanding of 3D space, generating, reconstructing 3D space, but also completely different structures that people struggle with, proteins, molecules, relational databases, internet, social networks, right? So these are areas where there is a dramatic need for better AI algorithms. And the biggest challenge typically hinges on extending the powers of convolutional and similar networks to non-Euclidean structures.
Okay, we don't have further questions from the audience, so then I will finish with actually a last question. Because you mentioned your love for mathematics and theory, and the best applications are based on good theory or practical theory. So maybe since this is very, very general with directed graphs, would this maybe also have applications towards more computer science theory and maybe even towards P and B problems?
Yes, I do believe so. This is a fascinating challenge. In computer science, there is a lot of, I'm not really a computer scientist by formation. My background is in physics and mathematics, but I've spent enough time in computer science to understand what are the core challenges a lot of my colleagues are focusing on. And obviously, one of the most central challenges is often the question of how efficiently can I compute something? Can it be computed in polynomial time or polynomial time approximation schemes are there? Can I approximate the solution in polynomial time? Is it problem in p-hard? Is it not, etc.? So these are a lot of fascinating challenges. I'm not sure that AI and machine learning will help to answer these challenges, but what we are seeing already is that they often provide solutions that are significantly faster than established algorithms, that you can deploy AI and neural networks inside systems. And this holds not just for computer science, but for all of physics, right? We have published papers where we showed that if you do weather simulation, for example, typically you would revert to numerically tedious Navier-Stokes type simulators. But it turns out you can train AI modules to dramatically accelerate. They just predict the output based on training data, right? And although that prediction may not give you the perfect solution, the speed up can be massive, right? And so I think this is also the future for weather forecasting and possibly other types of forecasting where classical numerical simulations are just too computationally demanding. And where a neural network can give you a dramatic boost in speed and give you possibly a much better trade-off in terms of speed and accuracy. And we are currently exploring in a new project how these kinds of AI algorithms can help to improve the performance fusion reactors, right? This is a company in Munich that does fusion, Proxima Fusion, and we have a joint project that's starting now where we want to look into, can we use AI to accelerate the numerical simulations?
Great. We actually got the last question from the audience. So Cem Uyuk saying, how would the approximation of spectral decoding for directed graphs translate to vision beyond scene understanding and synthesis? Specifically, I'm looking for could it enable reinforcement learning for robots for interaction?
Ooh, that is not an easy question to answer, because I think this is quite a bridge from directed graphs and convolutional filters on directed graphs to reinforcement learning. Obviously, the neural networks that I've been talking about, they are employed heavily in the field of reinforcement learning. And this is one of, I would say, the hottest topics in robotics these days. And I find it quite a fascinating topic. To what extent directed graphs play a role in reinforcement learning and in robotics, I do believe they do. If, as I said, once you have this glasses of a directed graph researcher, you will see directed graphs no matter where you look. And so I'm actually quite positive that also in robotics and in this area of reinforcement learning, directed graphs will play a role. And then these convolutional filters will likely also play a role.
I mean, for example, you have also the Markov decision processes, which are also can be described as graphs and are
exactly
like basis of RL could probably help there as well.
That's a good point. Yeah, that's very true. Yeah.
Yes. So that actually brings us to the concluding part of this session. So I want to thank again Professor Cremers from Technical University of Munich and also the Munich Center for Machine Learning, as well as the ELIS unit in Munich and the LIS node in Munich. And we're super happy to have had Professor Cremers as part of this AI for Good series, also from our side, from ELIS, the European Laboratory for Learning and Intelligent Systems. And yeah, that brings our session to a closing. And now I hand it over back to the AI for Good neural network.
Thank you very much, Arno. Thank you for sharing. It's been a great pleasure.
Thank you, Daniel.
Thank you, everyone, for joining.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.